This video is an introduction to what function notation is. Now, whenever somebody's talking about function notation, they're basically saying, where we're used to having functions say y equals, we're now going to incorporate the fact that we have an input. X is usually what you're calling the domain. We're going to take a domain, and if we input it into our function, we're going to get y as an answer. So the idea is that X is our input. It is the domain. It's what I need to know first. If I plug this into my function, which is why we call this an f of x, whenever we read that, we are going to get an output as an answer. Now, it might help you to go ahead and see an example. So an example of a function would be f of x equals 5x plus 3. Very simple function. This function is basically all values. If I pick something for x, I'll get one answer for y. And I can pick any number that I want to for x, but it's only going to have one answer for y, which makes this a function. I find this helps me out if I just think of this as a fancy way to write y. Now, the easiest way, I think, to see functions would probably be graphs. And this is example number 1, not number 2. Now, if you recall when we started talking about functions in another video, we started talking about the vertical line test. And if you do the vertical line test, you'll see that I can only have one input for one output in my function here. Now, if I tell you that f of x equals 0, what I'm actually telling you is that x is 0. So if I go over to this picture of my function and I find where x is 0, you'll notice that it only touches my picture at one spot. That happens at this coordinate 0, 4. So this function hits at x is 0, y is 4, which means that f of 0 is the same thing as the number 4. Let's try another one. Now this time x is going to be a 1/2. So if I take my function and I take a look at where x is 1/2, you'll notice that it hits this yellow function in one spot, which is right here. Now that's going to have to be estimated a little because I don't really know what point this is, but that would be estimated to be about a 3.5. So using this picture, I could tell you that for an input value of 1/2 on this function, I would have to have a y coordinate of 3 and 1/2. Now this last example, same thing. If we have a -2, I end up at a coordinate of -2, 2. Which means my final function, f of -2, equals 2. Now, you won't always be given a graph. Sometimes you'll just be given the equation of a function. Now, this is an equation of a function that has nothing to do with the graph of the first example. I did use the same x values, but we're going to be looking at the equation for the function of f of x equals 2x squared plus 7x. Now, instead of being able to graph this and take a look at what my y values are going to be, what we're going to need to do is substitute in my different x values. So that when I evaluate this function, what I'm really going to do is just turn it into a number. Now, f of 0, that tells me that x equals 0. So, if I've wanted f of 0, I'm just going to make all the x's that I see 0. Now, if you take 2 times 0 squared, you get 0, and 7 plus 0, or plus 7 times 0, which is equals to 0, has been evaluated to the number 0. Now let's go ahead and take a look at this next one. F of 1/2. I'm going to take the exact same function, only instead of a 0, I can just pick a different x, and I'll get 1/2. So now we'll have 2 times your 1/2 squared plus 7 times 1/2 equals. Now, a reminder, if I want to square 1/2, what I'm really saying is 1/2 times 1/2. Now, if you multiply the numerators, you get 1, the denominator, you get 4. So 1/2 squared is just 1/4. So what I have is 2 times a 1/2. Sorry, we have a 2 times a 1/4. Now, reminder, fractions. If I'm multiplying two numbers together and one of them's a fraction, I need numerators and denominators, just like we had over here. So 2 times a 1/4 is going to be a 2/4, which reduces to a 1/2. And that's how we would get this first section. So we end up with a 1/2 plus 7 times a 1/2. I do the same thing, and I end up with 7/2. Now that we have common denominators, because we're adding our two fractions together, 1/2 plus 7/2 is going to give me 8/2, or 8/2, which is the number 4. So if I was to take a look at this function, if I plug in a 1/2 for x, my y would have to be 4. Now the last example. This time I'm telling you x equals -2. Now the reason I did this one is because if we plug in a -2 for our functions, we get f of -2 equals 2 times -2 squared plus 7 times -2. And I find my students tend to get confused about what happens with all of these negatives being multiplied and squared. So I want to take a look at this part specifically. If you just focus on the -2 squared, what I'm telling you is -2 times itself. So we're going to take a -2 times a -2. Well, if I have two negatives being multiplied together, that's a positive. 2 times 2 is 4, so this is going to become a 4. So what I have is 2 times 4. Then 7 times a -2 is going to be a -14. If you take 8 minus 14, you're going to get the answer of 6. The last example is going to be using our function notation as part of a word problem. So let's take a look at this one. We have a Japanese bullet train that travels from Tokyo to Kyoto at an average speed of 156 kilometers per hour. Now the distance from the two cities is approximately 380 kilometers. Now the first thing they want us to do is write a function to represent the distance left to travel as a function of time. Now you have to be able to read all of this to be able to do this problem. Not necessarily the easiest thing to translate. Now we want a function to represent the distance. Represent, I hope we all remember, is another way to write equals. So I want a function that equals my distance. So this is going to be kind of like my f of, and you'll notice that this says function of time. So the time is going to be inside your parenthesis. Now the trick to this one is we've got the distance left, a total distance, and what I've already covered. Now let's just kind of go through this as a logical progression. I'm thinking that the distance left is going to be the total distance minus what I've already traveled. Okay. So if we went ahead and wrote this in function notation, the distance as a function of time, so we have d of t equals, Now the total distance, I'm going to go ahead and get from my word problem, which is 380 minus the distance I've traveled. Now, we need to remember how to find the distance. Now, to figure out how far you've gone, all you have to do is take your rate times the time you've been doing that. So, I just need to take r times time. Now the next part of this question says, what's the value of the function for an input of 1.5? Now what this is telling you is that you've been traveling for 1.5, because that's the input of your function. So if I wanted to know the distance after 1.5 hours, I would end up with 380 minus, now my rate is also in my word problem. I probably could have put that here. So let's go ahead and do that. 56 times time. So we have 156 times the 1.5. And now to evaluate this, the entire right side is numbers, so it's just a matter of punching things into a calculator, and what you end up with is 146. Now, the big question for letter C is 146 watts. In order to do that, you'd need to look back and say, my distance that I had left was supposed to be my answer. So this 146 means that I have 146 kilometers to still travel. So I think a nice, easy way to write that is there is 140 kilometers left. 146 kilometers left. Okay. When dealing with function notation, just remember that a function, f of x, is really just a fancy way to write y. Throughout class, we're going to go over several different examples. It looks really scary, but don't be scared. It's a pretty easy concept once you get it.